In today's statistic lesson, we will be discussing hypothesis testing for a mean when the population standard deviation is known. Please take a moment to press pause and read through today's objectives. All right, so just to remind you from our last lesson that when you are using the p-value method in hypothesis testing, that if your p-value is less than alpha, less than or equal to alpha, you are going to reject the null hypothesis. And if the p-value is larger than your alpha, then you will fail to reject. All right, so let's just practice that little piece for now. All right, the p-value for the hypothesis test is 0.0237. What is your decision? So you compare your p-value, which is 0.0237, and you're going to compare that to your alpha in the first question, which is 0.05. Notice that the p-value is lower. So the p is low, the null must go. So you will reject the null, whatever that might be in this case. All right, repeat that process with the second one. Look at your p-value, look at your alpha. In this case, the p-value is larger. So since the p-value is larger than alpha, then we're going to fail to reject the null. And that's how you will draw your conclusion from the p-value. All right, remember that when you're doing your hypothesis test, make sure that you are getting the correct p-value. If it's a left tail, you will take the area in the left tail. If it's a right tail, you take the area in the right tail. If it is two-tailed, you will find the area in one of the tails and then multiply it by 2. So just remember, you have to make sure that you're doing the right kind of test. All right, so this says find the p-value for the left-tailed hypothesis test. So here's my picture. Here's my standard normal curve. It's a left tail, and it's telling me that this area right here, we need to find this area given the fact that the test statistic, so this z-value right here is negative 2.23. Right, so I will go to my chart and I will look up the value of that area for the corresponding z-score. And it turns out that this p-value for that tail is 0.0129. All right, so we will now compare that to our significance lever, so our alpha, which is 0.01, and in this case the p-value is slightly larger than the alpha, so that means we will fail to reject our the p is higher, so we're going to fail to reject the null, whatever the null happens to be in this case. All right, so let's have you try one. So give this one a read and see if you can figure this one out. All right, let's see how you did. Okay, so this one is a two-tail, so I would draw my picture. I'm going to have a two-tail. So this time my p-value is spread over both of those, and it tells me that the test statistic is 2.14. And if this is 2.14, then this test statistic over here will be negative 2.14, because remember, everything is going to be symmetrical. All right, so if I find this area and this area are exactly the same, so I'm going to find this area because that's what's easier to find on my chart. So if I go to my chart, I would look up that area, and it turns out that area right there is 0.0162 on my chart. All right, so because I have two of them, I have to multiply that by 2. So my p-value is 2 of 0.0162, which turns out to be 0.0324. And then you're going to compare that to your alpha, which is 0.05. Notice the p-value is lower, so we should reject our null in this case. All right, so that's kind of the end of the hypothesis testing. So I just wanted you to see that final product. All right, so now how do we find these z values, right? These z test statistics that they were giving us. Okay, so that's our next step. How do we do that? So the z test for the mean is just a statistical test that uses the sample mean X. So when you're doing this test statistic, you will need to know these sample mean. You will need to know the mean of the population, which should be given to you in either the null hypothesis and the alternative hypothesis. You will need to know the standard deviation of the population, and you will need to know your N for your the number of data points. And then you'll need to make sure that your sample is random, and you will need to make sure that one of the following is true. Either it's normally distributed or N is greater than or equal to 30. And just remember that this adjustment in our standard deviation comes from that central limit theorem and our standard error of the mean that we talked about in a previous lesson. All right, so if you're going to use p-values, and don't worry, we will do the critical value method as well. So if you're going to use p-values, here are your steps. And again, you can press pause and write these down. But we are going to go through all these steps. We're going to verify that we know the standard deviation of the population. We're going to verify that it's a random sample, that it's normally distributed, or it's greater than or the sample size is greater than or equal to 30. We're going to state our null and our alternate. We're going to identify our alpha. We are going to find that test statistic. We are going to find the area that corresponds to that. We're going to find that p-value that we need, and then we're going to decide to reject or fail to reject, and then we're going to write out our claim. So we are going to do these problems all the way through from beginning to end using these 8 steps. All right, so here is our first one. In auto racing, a pit stop is where racing vehicles stops. They stop for new tires, fuels, repairs, adjustments, anything they should need. The efficiency of the pit crew that makes these adjustments can affect the outcome of a race. So having a very fast pit crew is very important. So a pit crew claims that its mean pit stop time for 4 new tires and fuel is less than 13 seconds. So that is their claim. All right, so I'm going to write that over here. Their claim is that their mean time is less than 13 seconds. Okay, because that does not have an equal sign, that's definitely going to be my alternate hypothesis. My null hypothesis would then be that mu is greater than or equal to 13. All right, it says a random sample, so they already told us it's random, excellent, of 32, so my N is 32 pit stops, has a sample mean, so there's my X bar, of 12.9. Assume the population standard deviation, all right, there's my sigma is 0.19. All right, is there enough evidence to support? All right, so here we go. And they're telling me the alpha. The alpha is 0.01. Okay, so we have to walk through the whole process and see what we can see. Okay, so I have my claim, I have my alternate, I have identified my alpha, excellent. The next step is to find that test statistic. Okay, so let's find that. The z is equal to x bar minus mu over the standard deviation divided by the square root of n. So let's plug all that in. So that's going to be 12.9 minus 13 divided by 0.19 divided by the square root of 32. And I'm going to put all that in my calculator, and I get my test statistic to be about negative 2.98. Again, remember z is rounded 2 decimal places. Okay, so this is a one-sided test. Notice because my alternate is strictly less than, it's going to be a left side, so it's going to look like this. It's going to be a left side. That right there in the shade is going to be my p-value. So this z right here is equal to negative 2.98. So I would go to my charts and I would look up this area. That area right there is my p-value. And when I go to my chart and look up the area that corresponds with negative 2.98, I get 0.0014. And that is definitely less than my alpha, right? Significantly less than my alpha. So that means the p is low, the null must go. So I'm going to reject the null hypothesis. I'm going to reject this. So I'm rejecting this right here. So if I'm rejecting that, then that means that I'm going to say that there is enough evidence to support the claim that the mean pit stop time is less than 13 seconds. And again, if you do get stuck, please refer back to the previous lesson when I gave you that nice flowchart that told you exactly how to answer it using words. So practice with that flow chart, and that should definitely help. All right, let's do another one with the p-values, and then I'll show you the other method, the critical value method. All right, so according to a study of U.S. homes that use heating equipment, the mean indoor temperature at night during the winter is 68.3 degrees Fahrenheit. Okay, you think this information is incorrect. You randomly select 25 homes. Okay, so there is their claim. Okay, so let's start with the claim. They're claiming that the mean indoor temperature is 68.3 degrees Fahrenheit, and that is definitely the null. Okay, so the alternate is going to be that the mu is not equal to 68.3. All right, we randomly select 25 homes, so that's my n. My n is 25. Find the mean, and we find that the mean indoor temperature, so the x bar in that sample, is 62.7 degrees. And from past studies, the population standard deviation is known to be, so there's my sigma, 3.5. All right, the population is normally distributed. Check, that's good to know. Is there enough evidence to support your claim at alpha equals 0.05? Okay, so there is all the information that we gleaned from the problem. All right, so let's start with, oh, and there's our claim. I already have that labeled. Okay, so let's start with our z. Let's find our test statistic. And again, write the formula x bar minus mu over sigma divided by the square root of n. So that's going to be 67.2 minus 68.3 divided by sigma over the square root of 25. Oh, and the sigma, I forgot to write what sigma was. Let me erase that. All right, so my sigma was 3.5. All right, so I'm going to put all that in my calculator, and when I round to 2 decimal places, I get negative 1.57. Okay, so this is, notice my alternate, this is a two-tailed, so if I draw the picture, this is two-tailed. So the area in both of these will be my p-value. My z test statistic is negative 1.57, so this is positive 1.57. So my p-value is twice whatever this area is here because these two are identical. So my p-value is going to be twice whatever that is. So I go to my chart and I look that up, and that is 0.0582. So multiply that by 2, I get 0.1164. And when I compare that to my alpha, not sure why my pen just stopped working. Sometimes I think my pen has a mind of its own. There we go. I'm going to compare that to my alpha, which is 0.05. This is definitely, the p-value is definitely larger. So I'm going to fail to reject the null, which is the claim in this. So I cannot reject this. So there is not enough evidence at the 5% level of significance to support the claim that the mean indoor temperature at night during winter is different from 68.3. So their claim, I can't disprove that their claim is wrong. All right, so now that we've done p-value a couple of times, let's do the other way that we could do hypothesis testing, which is using critical values or rejection zones. So again, let's just review that a little bit. So you're going to find the range of values for which the null hypothesis is not probable. And the way you're going to do that is by finding those critical values, which come from your alpha. So you're going to draw your picture, label your alpha in the picture, and then find those critical zones. And then once you do that, then you can identify. So let's show you some pictures. Okay, so you find your alpha. So if it's a left-tailed test, this will be your alpha on the left. And then if your test statistic falls within that area, you would reject the null. If it falls in the area over here, where the data is probable, then you would fail to reject. Okay, if it's right-tailed, same thing. All your alpha is going to be on one side. And then, so if your test statistic falls here, you would reject. If it falls here, you would not. And then last but not least is your two-tailed. Make sure that you cut alpha in half, because half of it has to be over here and half of it has to be over here. So your test statistic could fall in either of these rejection zones, or it could fall in the center. So it's really important that you really draw that picture so you can visualize what's happening. All right, so let's just start with focusing on critical values. Okay, so find the critical value and rejection region for a left-tailed test with alpha equal to 0.01. Okay, so a left tail means we're going to look like this, and this area here is going to be our alpha, which is 0.01. So we will then need to find the critical value right here, which obviously is going to be negative, right? So I would go to my chart, I would look up when the area is 0.01. So you're going to go inside the table and then find the z-score that corresponds to that. And in this case, the z-score that is closest is negative 2.33. So that would be my critical value. So when I do my test statistic, I would see that it would either fall here, which is the fail to reject, or the shaded area, which is the rejection region. All right, here's the next example. Find the critical value and the rejection region for a two-tailed test with alpha equal to 0.05. Okay, so this time, when we draw our picture, we're going to have a two-tailed test. And the alpha, half of it has to be here and half of it has to be here. So that means this area is 0.025 and this area is 0.205. And we need to find those critical z's right there and right there. Remember, they're going to be the same number. One's going to be positive, one's going to be negative, right? Because we're for each tail. All right, so I would go to, I'm going to use this one on the left because I think that's easier to find this. So I'm going to go into my negative z score chart, and I'm going to find the area of 0.025 inside the chart, then inside the table, and find out what corresponds to that, and that would be negative 1.96. So that means this is positive 1.96. So my rejection zones are greater than 1.96 if my test statistic is greater than 1.96, or if it's smaller than negative 1.96. If it's in between those two values, then you would fail to reject your null. All right, so those are your rejection regions, right? Reject, reject, reject if it's either of the tails. So basically, if it's in the tails, you're rejecting it. If it's in the center, then you're not going to reject. Okay. So these are the steps for working through a rejection region problem. Again, feel free to press pause, write anything down that you need to write down. All right, but the steps are pretty much the same as they were before. So we're just going to do a couple of problems where we do the rejection region method. Please note for my students that you will definitely have both of these on your test. So please make sure on your quiz. So please make sure that you understand both methods because you will be expected to do both. All right, so employees at a construction company and a construction mining company claim that the mean salary of the company's mechanical engineers is less than that of one of its competitors, which is $95,600. Okay, so they're claiming that the claim is that the mean salary is less than $95,600. Okay, that is definitely not the null, that's definitely the alternate. Okay, the null would be mu is greater than or equal to 95,600. Okay, so this is definitely a one-tailed test, so you can draw that picture now if you want to, because we know our alternate is less than. So I can draw that picture. This is going to be my rejection zone. Okay, so let's write down all the important information. So it's a random sample of 20, so n equals 20. The sample salary that they found from those 20 is $93,300. We assume the population standard deviation, so there's my sigma, is 9,500. And the population is normally distributed. Excellent, so we can do this. And my alpha is 0.05. So that means this area right here, that is 0.05. So we need to find the critical value right here, so that we know when our test will be rejected or not. So I'm going to go look up an area of 0.05 in my table, and I find that that gives me a critical value of negative 1.645. All right, so now I need to find my test statistic and find out where that falls. So my test z, remember, is x bar minus mu over the standard deviation divided by n. So we're going to plug in everything we know. So our x bar is 93,300 minus the mu, which was 95,600, divided by the standard deviation, which is 9,500, which is also then divided by the square root of n. So my test statistic turns out to be, when I put that on my calculator, negative 1.08, which is above, right? It would be right here. My z would be negative 1.08. So notice the z falls in the non-rejection zone. So we will not reject. We fail to reject. And there my pen goes again. There we go. Fail to reject the null. So this is my null. And I can't say that, so I have to assume that that is correct. I don't have enough evidence to reject that. So if that is the case, then I definitely don't have enough evidence to support my claim. All right, so there is not enough evidence to support. So if you want to write a full sentence, there is not enough evidence at this 5% level of significance to support the employee's claim that the mean salary is less than $95,600. Right, so again, make sure that you are being able to write your answer very clearly. All right, let's do one more just to make sure we got this rejection region thing under control. All right, a researcher claims that the mean annual cost of raising a child between the ages of 1 and 3 is $13,350. So there's my claim. The mean is $13,350. All right, that is definitely my null because it's got the equal to, and my alternate will be that mu is not equal to 13,350. So this will definitely be a two-tail. So I'm going to draw my picture, draw my two tails, right? This area and this area are my rejection regions. Okay, so let's read the rest and get the rest of the information. In a random sample of families in the US, the cost of raising a child between the age of 1 and 3, okay, so there's my X bar, is $13,186. The sample consists of 1,000 children, so there's my N is 1,000. It says assume the population standard deviation, excellent, is 2,750, and that your alpha is 0.10. So at alpha equals 0.10, is there enough evidence to reject the claim? Okay, so 10% is our alpha, so that means this side is 5% and this side is 5%. You got to break up that alpha on each side. So we should be able to find that critical value very easily by looking at our chart. So I go to my chart and I look for an area of 0.05, and that tells me that is negative 1.64. So there is my critical value cutoff. So that critical value tells me my rejection zone versus my non-rejection zone. And that would also be the same critical value over here, positive 1.645. All right, let's do our test statistic and find out where it falls. So X bar minus mu over sigma divided by the square root of n. So X bar is 13,186 minus the mu, which is 13,350, and then divided by sigma divided by the square root of 1,000. So I put all that in my calculator, and my test z statistic comes out to be negative 1.89. Notice it will fall in the rejection zone this time. Negative 1.89 would be here. It'd be lower than negative 1.64. So we are in the rejection zone. So we are going to reject the null, which is my claim, right? My claim was the null. So when you put this in words, you're going to say that we are going to reject the null hypothesis, which means that there is not enough evidence to support the claim that the mean cost to raise a child between the ages of 1 and 3 is $13,350. I don't know if it's more, I don't know if it's less, I just know it's not $13,350. All right, so those are the two different methods from beginning to end. Hopefully this clears up any confusion you had from the previous lesson where I tried to talk about each step. Once you see it all cohesively, it really flows very nicely, and you can walk your way right through it. So the important part is just picking out all the information that you need and doing the steps in the right order. So make sure you really review the steps and make sure that you're doing everything that is needed. All right, so come back next time. We're going to talk about how do we do these tests if we don't know the standard deviation of our population. So come back next time.